All right, here's our final part of nutrition here, Nutrition 03, and we're going to lead off by our last metabolic pathway, that is protein metabolism. Protein metabolism, yes, we can think about it in terms of how do we break down proteins into ATP, but that's not really something we do a lot of. That, as we've kind of mentioned before, it's really a last-ditch, try not to die, desert island kind of thing. So when we talk about protein metabolism, here we're really talking more about how do we use proteins, how do we build proteins, how do we replace worn out proteins, because they are structural and functional in our body in ways that carbs and fats really aren't. Okay. One big problem we've got is that proteins over time, we use them, right? They deteriorate, they break down. And so to maintain, to say nothing of growing, we have to continually catabolize them and then anabolize them, break them down and replace them. For the most part, if we can, we recycle your amino acids, right? We can make new proteins out of them, sometimes the same protein, or sometimes a different a different kind of protein, or maybe we use them to build, say, DNA, or we use them to build a hormone, or we use them to build ATP or whatever else. But the key here, again, remember, is that we don't store them, right? So we have that all or none rule. So as we break down a worn out protein, if we can't use the amino acids to build something new out of it, it leaves your body one of a couple of different ways. You break it down for energy and excrete the remaining parts in your urine. We can convert excess to fat, right? We have that acetyl coenzyme middleman, right? So we can hop pathways and go back to lipogenesis. Depends on what we do a lot of, but we can do it. Protein synthesis, this is what we do most of the building, right? When we talk about building things in your body, we talk about anabolism. It's amino acids, right? We don't generally do a ton of building of other things outside of glycogen, right? And again, remember, we have to have all of our essential amino acids in order to make this work. In your lifetime, the average person, now again, I point out that the average person here for all of these studies is a male who is 5'6" and 160 pounds. I do not know a single 5'8", a single 5'8", 160-pound man. I don't think I've ever met one in my entire life. So these numbers will vary, obviously, with person to person. But you know, somewhere in the several hundred kilograms of protein range is what you can expect to make during your lifetime. So we do a lot of protein synthesis, I guess, is what I'm coming down to here for you. The degree to which you are breaking down old proteins and rebuilding new ones, we refer to as the catabolic, right, the breakdown, catabolic-anabolic, or building steady state. Okay, and this fluctuates, it's dynamic, it goes up and goes down as your body's needs change from hour to hour and day to day. But basically, this is the idea, right, that you are continuously tearing down and rebuilding your body. Okay, largely, again, proteins, okay, but also other nutrients, other things for different purposes, right? And so we need to kind of consider all three of our major nutrients here as different nutrient pools, different sources for the raw materials to build things, right? But also places to take the catabolic waste products and dump them, right? So you've broken something down and now you've got amino acids. You've broken something down and now you've got carbs, right? Where do those things go? They go back into the nutrient pools. So we're pulling them out, or putting them back, pulling them out, pulling them back. Again, because of acetyl coenzyme A, and I feel like I'm saying this a lot, right? But I'm saying it a lot because it's important, remember it. Because of acetyl coenzyme A being the middleman in all of our different metabolic pathways, we can convert any one of these into a different form, right? We convert an amino acid into a carb or into a fat if we need to, or a carb into amino acid, or a fat into a carb, whatever, okay? The amino acid pool kind of sits on its own because it's, yes, we can convert it to other things, but it's hard, right? We really, really, really don't do it. We don't have to. For the most part, the amino acid pool sits by itself and is therefore the raw material for the making of new proteins and is a storage depot for the, well, storage is the wrong word, but a short-term drop-off point for broken down amino acids. Okay, so we can reuse them a little bit later on. We are continuously losing proteins because, again, we don't store them. So shed skin, shed hair, nail clippings, your urine, okay, all places where we lose these things continuously. So we do have to kind of continuously refresh them. The carbs and fat pools, however, again, they're a little bit closer, right? They're a little bit more interleaved. They're easier to convert from one to the other than a protein is to any of the above. Okay, so they're much more closely linked. And again, remember, where are these things linked through here? Primarily acetyl coenzyme A. Okay, so with that in mind, right, this idea that we've got these three different nutrient pools that we can add to or remove from, okay, this gives us this catabolic-anabolic steady state of your entire body. Okay. And ultimately, what this represents for us is the shift back and forth between what we're going to call an absorptive state and a post-absorptive state. Are we actively adding nutrients to our pools, right, as we do in the absorptive state, or are we pulling them out of these pools for use, which is what we do in the post-absorptive state? And basically, this sort of revolves around whether you've eaten recently or not. Okay, so on average, right, if you eat 3 meals a day, and I know that you're all eating 3 square meals a day, especially now, right? But if you're eating 3 square meals a day, you spend around 4 hours during and after a meal in the absorptive state, where you're actively bringing in nutrients from the food you just ate. So 3 times 4 is 12, which is half of the day, right? One of the reasons we talk about having 3 meals a day means that you spend 12 out of 24 hours in the absorptive state. The remainder of that time, okay, so when you are not in that absorptive state, you're in the post-absorptive state. So late morning prior to lunch, late afternoon prior to dinner, all night, okay, you exist in this post-absorptive state where you are pulling things out of reserve, right, and using them to meet your nutrient requirements during that time. The absorptive state is primarily controlled by the hormone insulin, right? And insulin is something that's going to cause you to start storing nutrients for later on, right? So you've had a big meal, you've got all this stuff kicking around in your bloodstream now. It's too much for what you need in the moment. Put it away, let's put it in the pantry, let's put it in the savings account so we can have it for later on. So primarily here we think about blood glucose levels, but also high levels of amino acids. So if you have a protein-rich meal here also, you can produce a bunch of insulin as a result. Post-absorptive state here, this is not about storing, but pulling things out of the pantry, pulling things out of the savings account. And so here we think primarily about hormones like, what am I looking for here? Glucagon, a handful of other hormones that are involved in removing things from storage. Mostly we worry about glucose because of your nervous system's reliance on it. Other tissues in your body can make do, can find their own way, but blood glucose has this outsized importance because your nervous system can't run anything else. So there must be a fairly stable, consistent amount of glucose in your blood, regardless of whether you're in the post-absorptive state or the absorptive state. That's really, really vitally important for us. So where does glucose come from? Obviously, you can get it from your body, or from your diet, right? You bring it in. But if you're in the post-absorptive state, where is it going to come from? Glycogen and the breakdown thereof, so glycogenolysis, okay? Lipolysis, if we need it, right? We can break down fat into glucose if we have to. If you're on a desert island, you can turn proteins into glucose if you have to. But we would really prefer not to. Other things that are going to be important for us in this post-absorptive state, right? Basically, the more efficient we can be during the absorptive state, the better off we're going to be in the post-absorptive state. The reason for this is that as long as insulin is being produced and is being put out there, we are not capable of shifting into the post-absorptive state. The reason this becomes important here for us is that sometimes we can run into a situation where we need to start pulling things out of storage, but we've still got insulin putting it in. So one thing that you can do, and again, if you're underage, please don't, right? Although drinking age is a matter of debate, I guess. But if you're sitting down to a meal, go ahead and have a drink, right? Have a beer, have a glass of wine. If you are, I guess, a sailor in the British Navy, have some gin, whatever you got to do. That alcohol can actually cause you to store excess glucose without insulin, which makes the transition from absorptive to post-absorptive state an awful lot smoother, believe it or not. So having a drink on occasion is not necessarily a bad thing. As I mentioned before, the major hormone here during this post-absorptive state is glucagon. This is something that we're going to release to start pulling glucose out of storage so we can use it when we don't actively have it being added to the bloodstream from absorption. One issue that we might have, if we go back to what we said about insulin being released in response not just to high carbohydrate intake, but also high protein intake. If you eat just protein, so if you go to Texas Roadhouse, and I love Texas Roadhouse, no shame there at all. You go to Texas Roadhouse and you order a big ass steak and you just eat the steak. You don't have any of the sides or any other stuff that goes with it, you just have the steak. Basically what you've done is you've dumped a bunch of protein into your system with no carbohydrates. So you're going to release insulin, but you're not having any carbohydrates. So that insulin is going to take what little blood glucose you have and put it into storage. And so you can end up with hypoglycemia. Now, in our scenario here, right, this is just going to make you cranky, right? You're going to eat a Snickers like the commercial, right? If you're on a desert island and you are eating only fish, right, or only meat of some description, and you're not eating any plant products, any sugars, you can actually suffer brain damage from this. So again, it's important to have nice balanced meals when you can. Why you get kind of irritable and cranky and all these things with these low blood glucose levels is that it's the release of emergency sugars from fats is tied to your sympathetic nervous system and your fight or flight response. Okay, and all of the things that go with that, the sort of the stress response, all of these things are tied into that. And so you turn into a cranky pants when you don't have enough blood sugar because you're running on fight or flight that whole time. There are a handful of other things here. I guess I'm not super concerned with this now as I sit here and read this. So let's not worry about this. Okay. So last little bit here, last 10 slides or so. We're just going to kind of clean up some little parts here, some missing little things here. The liver itself, again, we talk about the liver wearing so very many hats, doing so very many important things here. When we talk about it in terms of nutrition, we're talking about one particular part of the liver here, the hepatocytes, the cells of the liver, serve so very many metabolic functions. They're there to convert non-essential nutrients into other forms. They're there for storage of certain vitamins, certain minerals. They break down alcohol, they break down drugs, they break down hormones, they produce hormones, they produce bilirubin. Just a massively, massively, massively important thing. And of course, we can't forget, hopefully you can remember, the role here again, we're producing 85% of your body's cholesterol needs, which is a nice halfway decent segue, I guess, into the last part of this whole thing, which is cholesterol. Now, again, remember cholesterol, super important, right? It's not a bad thing at all. We need it to make bile. We need it to make steroid hormones. We need it to make vitamin D, okay? We use it to stabilize our cell membranes. All of this stuff, very, very important things. Because it's so important, your body devotes a big chunk of its energy, I guess, to making it, right? We don't need to eat a lot of it. We only need about 15%, right? Because again, 85%, the other remaining part is made by the liver. The problem, therefore, is when we exceed that 15%. When we have too much, right? It's got to go somewhere. And honestly, we don't have a lot of good mechanisms for getting rid of it. It tends to accumulate. So in order for us to properly use it, because it is a fat, we have to have a means of moving it around your bloodstream. Okay, and this is where lipoproteins come into play. So ultimately, when you go and you have a cholesterol count done, it's not really measuring necessarily directly the cholesterol, it's measuring the quantity of these lipoproteins in your blood, which gives us kind of a proxy for cholesterol just in general. And there are 3 different kinds of lipoproteins. When you have your cholesterol done, you'll get a count of all 3 of these guys. The more fats, the higher, the more fats, the lower the density. So we can talk about very low density, and high density lipoproteins. VLDLs are very low density ones. These are there to transport triglycerides out to the body. Okay, so they're responsible for the production of fat tissue, basically. Your LDLs and your HDLs are responsible for the movement of cholesterol. Your LDL takes your cholesterol out to production for hormones, for storage, or for membranes. Basically, they're not there to get rid of it, right? They're there to, LDLs are responsible for stored or retained cholesterol. HDLs, on the other hand, HDLs are there to get cholesterol to places where we can get rid of it, right? So if you've got extra cholesterol, HDLs are responsible for getting rid of it, okay? So very, very different purposes. So when we look at LDLs and HDLs, the amount of each of those things in your blood can tell you a little bit about what you're doing with your cholesterol. More LDLs, you're storing cholesterol. More HDLs, you're getting rid of it. So when you get your whole counts, this is what you're going to get back, right? You're going to get a total cholesterol. And again, remember, we'd like that to be under 200 milligrams per deciliter, right? Because above that number, we start seeing it stored or building up in your arteries, atherosclerosis. Your HDLs and LDL counts, on the other hand, right? These are going to be, well, again, they're variably important. Right? We like a high HDL, right? So anything above 60 means that you have a nicely proportioned response to excess cholesterol. Right? Remember, again, HDLs get rid of excess cholesterol. So if you've got a lot of this, that means that you're good at getting rid of it. You're not storing it. You're not getting it built up in your arteries. You're getting rid of it. LDL, on the other hand, because we don't get rid of it with LDL, we move it around, we store it. High LDL counts typically are suggestive of cholesterol deposits, atherosclerosis. Okay, so we want low numbers for LDL. Anything under 100, we're pretty happy with. Anything above 130, we're unhappy with. Anything in the middle is kind of where we're starting to worry a little bit. Okay. Now again, remember, cholesterol levels are mostly driven here by your liver. They make the same amount day in, day out, doesn't care whatever else is going on. Okay. The remainder then of your blood cholesterol level is thought to be driven by the fats that you bring into your body. Okay, saturated versus unsaturated. Saturated fatty acids, generally speaking, have two effects that are potentially bad. Saturated fats tend to stimulate your liver to make more cholesterol, okay, and they also inhibit HDLs. They prevent you from getting rid of it. Unsaturated fatty acids, on the other hand, and again, remember these are your liquid at room temperature fatty acids, are there seemingly to enhance the breakdown and the excretion of cholesterol, so the getting rid of the excess. So in theory, right, one is causing you to make too much and not get rid of it, and the other is helping you get rid of excess. Okay, this is the theory, right? Now, as we saw in the first video in this series, as we saw in the linked article in that series, this may or may not be as true as we thought. Okay. But it's still a good idea to not have a lot of saturated fatty acids in your diet. Even if they're not awful, they're still not good. And of course, the worst, the absolute worst of all are these trans fats, these oils, these unsaturated fats that we made saturated, turned into a solid, right? Margarine. These not only have the negative effects we associate with saturated fatty acids, but they also, beyond that, actually reduce HDLs. Okay, so they basically do the exact opposite of what we want fats to do. They're horrible for you. Please, please, please avoid margarines at all costs. Avoid trans fats at all costs, because they are horrible. They are absolutely horrible for you. One thing, and this is the last thing we'll talk about, one thing that you might have heard about a little bit as you maybe you study nutrition or you just kind of hear about it in the news or whatever, are these magical things, these omega-3 fatty acids, things that we find in things like salmon and trout. They're essential, right? The omega-3 here refers to the position of the first double bond in the fatty acid chain. We cannot manufacture a fatty acid with a double bond in this position, so they're essential. But they're actually really, really good for you. They have lots of really useful things. They tend to lower blood pressure. They tend to help reduce arrhythmias. They help lower potential for spontaneous clotting. They're just, in general, good for you. So they do have some valuable points to them. Okay, so that's nutrition. In the next set of videos here, we'll begin talking about some related ideas, the urinary system and the reproductive system, which actually share not only a kind of real estate, but share a lot of the same